So picture the tension of standing in front of a heavy steel safe. You've got this combination lock in your hand, right? And you know that if you miss by even a single digit, the whole mechanism just locks up completely.
Oh, yeah. It's totally unforgiving.
Exactly. And that incredibly high-stakes precision is, well, it's exactly what we force ourselves into every single time we interface with standard machine logic. Like, you stare at a raw IPv4 address, something super common like 192.168.1.1, and your brain just isn't equipped to hold that sterile string of numbers accurately, especially under pressure.
Right. I mean, it's a fundamental mismatch between human cognitive architecture and machine efficiency. Computers thrive on raw sequential data. They process those cold, hard digits effortlessly.
But we don't.
No, not at all. Human memory is associative. It's narrative. And it's highly vulnerable to momentary lapses. We're essentially trying to speak binary using a biological processor that evolved to, remember faces, stories, locations.
Which is why the two pieces of source material we are looking at in today's deep dive are so compelling. They don't just put a band-aid on this mismatch, they completely rethink the interface.
They really do. It's a total paradigm shift.
Right. They take those rigid numerical addresses and run them through a translation process that turns them into either literal magic spells or ancient Egyptian hieroglyphs, all while backing it up with this incredible mathematical guarantee against human typos.
The elegance here lies in how the code respects both the machine's need for absolute precision and the human need for context. But to secure the data, we really first have to understand the mechanics of the transformation, like how a system actually converts an IP address into something a human finds memorable, even if they have zero programming background.
Okay, let's unpack this. Because to a computer, 192.168.1.1 isn't four separate numbers separated by dots, right?
Right. That dotted format is already a minor concession to humans. Underneath, an IPv4 address is just one massive 32-bit integer.
Like just a single continuous block of zeros and ones.
Exactly, it's just one giant number. But if I hand you a 32-bit integer, which can be the number in the billions, your working memory will reject it immediately. Cognitive psychology tells us we can only hold a handful of distinct items in our active memory at once.
So the system can't just hand us the big number, it has to break it down.
Right. So the script performs a very specific slicing operation. It takes that monolithic 32-bit number and chops it into smaller, manageable pieces or chunks.
I'm looking at the math here, and if it's a 32-bit integer and the script needs to generate values between 0 and 31, well, 31 is exactly the maximum value of 5 bits of data.
You've got it. So the system is just carving that 32-bit mega number into sequential 5-bit chunks.
It's just slicing the pie.
Exactly. And because each piece is exactly 5 bits long, the math dictates that the resulting value of each chunk must fall somewhere between 0 and 31. It is literally physically impossible for a 5-bit chunk to represent a number outside that specific range.
Wow, okay. And that restricted range of 0 to 31 is the key, isn't it? Because it maps perfectly to human language.
Yes, precisely. Once you have a handful of numbers that will always be between 0 and 31, you can just swap them out using a dictionary.
It's basically a simple lookup table.
Right. The crypt we're looking at relies on an array literally called word total. It matches each of those 32 possible numbers to 32 classic magic spells from role-playing games.
It replaces an abstract, boring numerical value with a phonetic anchor.
Exactly. So if your 5-bit chunk equals 0, the script swaps it for the spell Mara. If the chunk evaluates to 16, it swaps it for Suka.
So instead of memorizing a sterile sequence of machine data, you are suddenly asked to memorize a string of incantations, like Mira Suka, whatever.
Right. It completely shifts the cognitive load.
It's kind of like taking a standard banking routing number, breaking it down into pairs, and assigning a specific catchy pop song to each pair. Instead of trying to recall a lifeless string of digits, you just mentally play a specific playlist. You're taking advantage of how the brain naturally anchors information.
That's a great analogy. It drastically reduces the cognitive load.
Yeah.
But relying on language introduces a completely different vector for failure.
Uh-oh. What kind of failure?
Well, human linguistic memory is highly associative, which is exactly why it is vulnerable to something called transposition errors.
Transposition errors, meaning we swap adjacent things around, right?
Exact.
I mean, I do this constantly. If I have to read out a string of characters rapidly, my brain sees the whole sequence, but my mouth executes them in the completely wrong order.
Yeah, it's a known psychological phenomenon. Your brain processes familiar words as complete chunks rather than individual letters. So when you hold multiple familiar words in your working memory, like suka and mera...
Right, my brain has already successfully loaded the vocabulary.
Exactly, the words are queued up. But when it comes time to output that data sequentially, the sequencing mechanism can easily slip.
Because both words are sitting right there in my short-term memory. They're equally valid, just waiting to be spoken or typed. So in the heat of the moment, I intend to type suka, then mera, but I accidentally output mera, then suka.
And in standard computing, that tiny transposition is catastrophic.
Wait, really? Just flipping two words?
Think about it. If you flip two segments of an IP address, the machine doesn't ask for clarification. It executes the command and points you to a completely different, potentially malicious destination.
Oh, wow. Yeah, it just blindly follows orders.
Right. And this is where standard error checking usually falls short. If the system only checks whether the input words exist in the dictionary, a transposed sequence will pass perfectly.
Because the computer just sees mera, verifies it's a valid spell, sees suka, verifies it's a valid spell, and lets you through, straight into the wrong server. It has literally no way of knowing you swap the order.
Exactly, which necessitates a robust security mechanism to verify the sequence, not just the vocabulary.
And this brings us to the really cool part. The script achieves this through a mathematical armor that the original text dramatically refers to as the Philosopher's Stone.
I love that name. The technical term is a weighted checksum, but yeah, Philosopher's Stone really captures the alchemy of what's happening here.
It totally does. But how does this mathematical armor actually differentiate between a correct sequence and a transposed sequence of the exact same words, like step by step, for someone who isn't a programmer?
Sure. It works by binding the value of the spell to its specific position in the sequence. It's a multi-step verification process that runs instantaneously in the background. Step 1. The system examines the sequence of chunks you've entered.
Okay.
It identifies whether a spell is sitting in an odd-numbered position, like the first or third slot, or an even-numbered position, like the second or fourth slot.
So the actual physical position becomes a variable in the equation.
Precisely. Now, step 2 applies the weight. If a spell's in an odd position, the system takes its numerical value and multiplies it by 1.
Okay, so times 1. The value remains unchanged.
Right. But if a spell is in an even position, the system multiplies its value by 2.
Okay, so every alternating slot effectively doubles the value of whatever word is placed there. Odd is times 1, even is times 2.
Correct. Step 3. The system adds all of those newly weighted values together to create a single total sum.
Got it.
And step 4, it takes that total sum, divides it by 32, and isolates the remainder. In computer science, this is called a modulo 32 operation.
So the system isn't really looking at the total sum itself, it's looking specifically for whatever is left over after dividing by 32. It expects a very specific remainder.
Yes, and we can actually test this logic right now against the exact transposition error you mentioned earlier.
Oh, swapping suka and mera.
Yep. Let's swap suka, which holds a value of 16, with mera, which holds a value of 0. Let's trace the math on the correct sequence first. So suka is in slot 1, mera is in slot 2.
Okay, I can run the numbers on that. Suka in slot 1 means it's in an odd position. Weight is 1, 16 multiplied by 1 is 16. And mera is in slot 2, which is an even position, so the weight is 2. 0 multiplied by 2 is 0. We add those weighted values together. 16 plus 0 gives us a total sum of 16.
Exactly. And that sum dictates the final remainder when divided by 32. Now, trace the math when the human makes a transposition error and accidentally flips the order. So now, mera goes into slot 1, suka goes into slot 2.
Okay, mera in slot 1, it's an odd position, so weight of 1, 0 multiplied by 1 is still 0.
Right.
And suka is now in slot 2, an even position, weight is 2. 16 multiplied by 2 is 32. We add those up, 0 plus 32. The total sum is 32.
Notice the divergence there. Simply by swapping the sequence of the exact same words, your total sum changed from 16 to 32.
Oh, wow.
Yeah. So when the system performs its modulo operation dividing by 32 and checking the remainder, the results will be entirely different.
The checksum fails and the system instantly rejects the input. That is brilliant.
It really is.
It's kind of like a highly meticulous bouncer at an exclusive VIP club. The bouncer isn't just checking if you and your friend are on the guest list. They are checking if you are standing in your specifically assigned VIP coordinates.
Exactly.
If you and your friend swap seats, Your combined weight in those specific coordinates no longer matches the venue's math. The bouncer immediately flags the anomaly and denies entry.
That analogy perfectly illustrates the mechanism. The alternating weights ensure that any two adjacent items that swap places will mathematically distort the total sum. It is just a brilliant way to catch human transposition errors with 100% certainty entirely behind the scenes.
But spells still rely on language, which means they rely on phonetic memory. And if you're stressed, you might mispronounce a syllable, or perhaps you just don't have an affinity for linguistic memory at all.
Which perfectly explains the pivot in the second piece of source material we are reviewing today.
Right, because it takes this exact identical mathematical architecture, the alternating weights, the modulo 32 checksum, and applies it to a completely different cognitive domain.
It replaces the dictionary of 32 phonetic spells with 32 highly distinct ancient Egyptian hieroglyphs.
We literally move from verbal incantations to carving visual symbols.
Yes, we're translating IP addresses into an I, a bird, an ankh. It's a massive interface shift.
It sounds so cool, but technically speaking, rendering an ancient hieroglyph on a modern screen requires significantly more complex data structuring than rendering a simple alphabet, right?
Oh, absolutely. It requires a leap in text encoding. Standard English letters and numbers, like the ones at a basic IP address, typically rely on 1-byte character encoding, like ASCII.
And a single byte is enough to represent 256 distinct characters.
Exactly. That easily covers your alphabet, your numbers, and basic punctuation.
It's a very small, very efficient footprint.
It is. But if you want to render the vast, complex visual lexicon of ancient Egyptian hieroglyphs, 256 characters won't even scratch the surface.
Not even close.
Right. So to accomplish this, the script utilizes 4-byte UTF-8 encoding. By using 4 bytes per character instead of 1, the system taps into a standard that can represent over 1 million unique code points.
So the script is reaching deep into the UTF-8 library to pull out these elaborate multi-byte visual symbols, and that completely changes how a human interacts with the data.
Completely. Instead of trying to memorize a sequence of sounds, you are presented with an 8-character mural code.
It shifts the cognitive burden from linguistic processing to spatial and visual processing.
Yes, and visual memory operates very differently than phonetic memory. Our brains are incredibly adept at recognizing patterns, shapes, and spatial relationships.
Right, because when you look at a sequence of hieroglyphs, you aren't just reading, you're interpreting a visual narrative.
Exactly. You might not remember the exact order of Sukumera, but you'll definitely remember if the scarab beetle was placed next to the pharaoh's crown.
Yeah, that visual sticks with you. And the best part is, despite this massive shift in the user interface, the underlying mathematical armor remains totally untouched.
The bouncer still works.
The bouncer still works. Because visually, a user might still make a mistake. You might accidentally carve or select the hieroglyphs in the wrong order.
Right, humans are still humans. But because the script still assigns a weight of 1 to the odd positions and a weight of 2 to the even positions, any transposed symbols will instantly alter the numerical sum beneath the surface.
So the system doesn't care if it's evaluating a magical spell or a 4-byte UTF-8 scarab beetle.
Not at all. It just runs the modulo 32 math, sees that the remainder doesn't match the checksum, and shatters the mural before you can connect to the wrong network.
It's an airtight defense against our own messy biology.
It really is. And it demonstrates a critical principle in system design. We do not have to accept the premise that security and mathematical robustness require a sterile numeric user experience.
You can have both.
Exactly. You can build systems that accommodate the associative, visual nature of human memory without sacrificing a single ounce of machine precision.
We adapt the machine to the human, rather than endlessly forcing the human to speak the machine's native tongue.
That's the main takeaway here.
I love that. I mean, we started with raw, invisible data, an IP address that would normally trigger immediate cognitive fatigue. We converted it into a 32-bit integer, sliced it into manageable 5-bit chunks, and mapped those chunks to deeply human concepts.
Whether that's the phonetic rhythm of magic spells or the rich spatial narrative of hieroglyphs.
And we wrap that entire translation in a weighted mathematical protocol that anticipates our psychological flaws. It expects us to transpose adjacent items, and it calculates a checksum that perfectly catches those exact errors.
It is just a phenomenal synthesis of psychology, mathematics, and creative interface design.
It really is, but, it leaves you thinking about the limitations of our current digital landscape. We use mnemonic tools in other high-stakes environments all the time.
Like the 12-word seed phrases used to secure cryptocurrency wallets.
Exactly. But those systems generally lack this kind of alternating weighted checksum specifically designed to catch adjacent swaps. And they rarely utilize purely spatial visual encoding like 4-byte hieroglyph.
That's a great point.
Yeah.
They're still relying heavily on standard linguistic memory without that extra layer of positional verification.
Right. So imagine if instead of writing down a dozen random English words to secure your digital assets, your cryptographic key was generated as a unique, mathematically verified virtual tapestry.
Oh, that's an interesting thought.
Like a specific arrangement of visual symbols in a memory palace, where the exact coordinates of every image act as a weighted bouncer. And it mathematically guarantees that if your memory slips, the system catches it instantly.
It would fundamentally change how we interact with secure data.
It totally would. So for you listening, I want to leave you with this. What other fragile, boring strings of numerical data in your daily life could be secured not by demanding perfect machine precision from you, but by translating the math into something beautiful, magical, and entirely error-proof?